This is my Lab 3 bar magnetism. The purpose is to familiarize students with calculations and experiments of magnetic fields and bar magnets. We're going to be measuring distance dependence and modeling 3D computations of magnetic fields. We're going to be using the Biot-Savart law, which is used to calculate magnetic fields, and these two equations that represent the magnitude of the magnetic field for bar magnets, which we use to solve for mu. And the procedure, you're going to start with a magnet and a meter stick or ruled tape, and you're also going to need your phone, which you'll have to download a magnetometer app. And the process we're going to go through real quick is just finding the magnetometer in your phone. So once you're in the magnetometer app, you're going to want to align it north so that the x is nearly 0. Then you're going to want to shift it up and down along that along the meter stick without rotating it, trying to find the maximum value for x. Once you do, you're going to slide a piece of tape onto your phone across the meter stick, and that'll be around where your magnetometer is. You're going to repeat this in the y direction. After flipping your phone 90 degrees, that's what the middle picture is, and once you have the two pieces of tape, that little X mark is where your magnetometer should be roughly. And then using that, we're going to be measuring distances for certain magnitudes of B to develop a distance dependence relationship. And we're using Tesla meter. That's what I used, and the magnitudes that I used are given down below. The initials and surroundings, the Earth's magnetic field and the bar magnet's magnetic field are the surroundings, and the system is the magnetometer in my phone. And for calculation purposes, the bar magnet is at the origin. Observations made during the experiment: when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And so here are the results. On the right you see a graph, and on the left are just all the values and the averages that we used in an Excel spreadsheet. And so basically what this means is that the ln of k is going to be equal to negative 0.2192. K will be 0.8032, meaning that mu will be 86.98 amps per meter squared. And so we were also asked to find the magnetic field at this point, d perp, and with a magnitude of d. So basically, after you find all of that, you will plug in all these values, and you will end up getting a magnitude of 45.45 for your magnetic field. And then we're going to try and replicate that using a coding. And so to the top, you see we're defining, using the Biot-Savart calculation, we're defining how to find the magnetic field. And then the rest of the code is basically just setting up observation points and drawing arrows, which is what you see below. And here to the bottom, the picture's more arrows of the perpendicular observation points. And then the top is the observation point similar to d perp, representing d perp. And here were the results. You can see all the arrows around the bar magnet representing the magnetic field. You can see how down the pole it goes the opposite way, whereas perpendicular it's going to the left, which is what we expect. And the magnitude we got was 1.144 e to the negative 3. So comparison, the computational magnitude was much smaller than the observed magnitude, which was likely an error in calculation somewhere. And for our what if questions, what if you hadn't oriented your experiment to compensate for magnetic north? Well, all of the components of the magnetic field vector would be off by some value that comes from the contribution in each direction of the Earth's magnetic field. And what if you were to stick two identical magnets together end to end? Well, I would expect the magnitude of the magnetic field to nearly double, basically, and we know it would increase in the direction of the two magnets. Possible errors: the x value was never truly 0 when we were supposed to rotate our phone we were supposed to make sure X was 0, and you could get pretty close, but you could never get exactly on 0, and so it wasn't perfectly aligned north, so there's still some value of Earth's magnetic field that wasn't compensated for, and the parts of the procedure that required you to move your phone without rotation was very difficult by hand, and it probably ended up off by a few degrees, which adds to that first error.